Okay, before we go on break, we're going to do some modeling with exponential functions. So what that means is we're going to take the exponential functions and apply them to real-world situations. And there's lots of ways to do this. Right now, we're going to focus on two types of problems. The first type of problem involves doubling time. In other words, how long it takes for something to get twice as big. So if you have some idea of how long it will take something, whether that's a population of a species, whether that's money in a bank account, whether that's the size of the known universe. If you know how long it will take to double in size, then you can use this function here to figure out some other information about it. So here's what we got going on. N of t, that's our final amount after a certain amount of time. It is a function of time, function of t. N sub 0 is our starting amount. We multiply by 2 because we are doubling it. And then we have this exponent that's going to tell us how many times it doubles. And that's made up of two parts. T is the time, and that can be in minutes, seconds, days, years, hours, centuries, any amount of time. And then A is the time it takes for it to double. And you'll see this note here at the bottom. The A and the T, they have to be in the same unit. So if T is a number of hours, A would need to be a number of hours. If T is a number of years, A would need to be a number of years. So really quick, just so it makes sense what's happening here. If I can get my pen to work here. Okay, so let's say we have a population of squirrels in a national forest, and maybe one of their predators goes extinct and they just take off. And every 10 years, they double in population. So A, in this situation with the squirrels, would be 10. And let's say you need to have an idea of how many squirrels there will be after 50 years. See where this is going, see what impact it might have on the ecosystem. So T is going to be 50. If you plug that into this function here, we have 50 divided by 10. So this exponent here would be 5. And what you would do is you would take the existing squirrel population, you would multiply it by 2 5 times, or by 2 to the 5th power. So the exponent tells us how many times something would double. So let's look at an example. This involves bacteria, and a lot of these problems do. But we have a bacteria population that doubles every 3 hours. So right here, A is equal to 3, every 3 hours. Initially, there's 1,000 bacteria. So that's our N sub 0, our starting amount is 1,000. And this is a three-parter. The first part says to write or to find a model. And a model just means an equation or a function to represent this. So we're going to take N of t, that's our final amount, that's our function notation, equals our starting amount, 1,000, times 2, because this is doubling. And then our exponent is t divided by a. We know a is 3. T is our variable, so it's going to be t over 3. That's our function. Part B, it says how many bacteria are in the colony after 15 hours. So to do that, we are going to set up our function, and we're going to plug that 15 in for t. So we have 1,000 again. It's doubling, and it's doubling at every 3 hours for 15 hours. So we have 15 divided by 3. Now we just work this out. So 15 divided by 3 is 5. So we have 1,000 times 2 to the 5th power, which is 32. Remember, we got to do the exponents first. That's a common mistake people make, is they accidentally multiplying the 1,000 by the 2 instead of taking 2 to the 5th power first. Make sure you do your exponent first, order of operations. So we multiply that 1,000 by 32, and we end up with 32,000. So 32,000 bacteria after 15 hours. Final part, part C. It wants to know, when will the bacteria reach 100,000? How long is it going to take? How many hours before this hits 100,000? So to do that, 100,000 gets plugged in for our N of t. That's our final amount. So we're going to start with 100,000 equals, back to our original amount, 1,000 times 2. And then our t is our variable. That's what we're looking for. We don't know how long this is going to take yet. So it's going to be t. We do know it doubles every 3 hours. So 3 is still there for A. So now we got to solve this. To do this, first we want to get rid of this 1,000, this number out front. That's going to simplify it, give us some smaller numbers to work with. We end up with 100 equals 2 to the t over 3. Now, another order of operations thing. Notice I was only able to divide by the 1,000 and not by the 2. Since the 2 has an exponent, you cannot divide anything by the 2 until that exponent has been taken care of. So here's where we are. 100 equals 2 to the t over 3 power. The problem we have is our variable is stuck in the exponent. We got to have a way to get it out because there's no conventional way to start isolating a variable when it is in an exponent. The only tool we have to do this is logarithms. So this is where logarithms come into play. What we're going to do is take a logarithm of both sides. And this, notice I didn't put a little base here. This is just a base 10 logarithm. Just a plain old logarithm. And honestly, the main reason we use base 10 logarithms for stuff like this is because any scientific calculator, even the low-end ones, are going to have just a plain old log button for log base 10. The other bases, it's hit or miss, but any calculator you use is going to have a log button, which would be log base 10. Okay, the reason we set this up, the reason we take the log of both sides, and just to be clear, we can take a log of both sides the same way we multiply both sides by 2, or take the square root of both sides, or add 3 to both sides. It's same principle. But the reason we did log of both sides is because we learned a rule with logarithms that if you have an exponent inside of a logarithm, you can pull it out front. So what we're going to do here is we got log 100 equals, we're going to pull that t over 3 out front. So it's t over 3 times log of 2. Now, our variable is no longer stuck. It's out. It's not in an exponent. We can work with it. We can solve for it. And now that's exactly what we're going to do. We're going to divide by log of 2 to get rid of it. Try to get t by itself here. So we have log 100 divided by log of 2, which is approximately 6.64. I'm going to round that to the nearest hundred. 6.64 is equal to t over 3. And so our final step is just to multiply that number by 3. And when we do that, times 3, times 3, those cancel out. T is approximately 19.93, or almost 20 hours. So after about 20 hours, our 1,000 bacteria becomes 100,000 bacteria. So make sure you've got some Purell handy. All right. Next type of problem we're going to do is a growth rate problem. And here, this is probably a more common type of problem. And it says growth rate, but you can do this whether something is growing or decreasing in size. All you need is the percent, the rate at which it is increasing or decreasing. So very similar setup here. We have n of t, that's our final amount. We have n sub 0, that's our starting amount. But here, we're multiplying by e, because here we're dealing with things that are growing exponentially, continually. And we learned in an activity last week that when things grow continually and are growing exponentially, this number e comes into play. So e is the number we're multiplying by, and our exponent is RT, rate times time. So just to make sure it's clear, time, same as usual. Rate, that is a percent expressed as a decimal. So if you had a 35% growth rate, you would put that into the problem as 0.35. So that's how you would use the rate. So let's do an example with this. This is also bacteria. I promise we will get some other types of problems. But here we're starting with 500 bacteria. That's our initial amount. So 500 is n sub 0. And this biologist is taking some samples, doing some research, and finds that the bacteria are growing at a rate of 40% per hour. So our rate is 40%, so that's 0.4 or 0.40. All right, we've got a four-parter this time. First, we got to find a function, a model for the number of bacteria after t hours. So that's going to be very similar to what we did on the previous example. We're going to have n of t equals our original amount, which is 500, This time it's going to be times E, and then to the R times T power. So R is 0.4 times T. 500 E to the 0.4 times T power. That's part A. Part B. What is the estimated count after 10 hours? So what we're going to do there, similar as before, we're going to plug in 10 for T and just work it out, see what we get. So 500 times E to the 0.4 times 10 hours. When we work that out, 0.4 times 10 is 4. So we have 500 E to the 4th, and that is something you'll have to put in a calculator. So if you give me a second, I will do that. And when I do that, I find that this amount is approximately 27,299. So after 10 hours, 500 bacteria growing at 40% per hour becomes 27,299 bacteria, approximately. Part C, we got to figure out when will this reach 80,000. So 80,000 here is our final amount. That's N of T is 80,000. So we're going to start with 80,000 this time. And we're going to say 80,000 is equal to our original amount, which was 500 E to the 0.4 times T, because this time we don't know the time. That's what we're looking for. We're looking for T. So same as before, you're going to divide by this first number to simplify a little bit. And when you do that, you should get 160 equals E to the 0.4 T. Now here, we're in the same situation where our exponent or our variable is in the exponent. So the only way to get it out is to take a logarithm of both sides. Here, since we're using E, instead of doing just a regular old log, we're going to do a natural log. We're going to do ln. So log base E. And you'll see why we do that in just a second. So the first thing we want to do here, though, is use our logarithm trick to take the stuff in the exponent and pull it out front. So we still have natural log of 160 equals, we're going to have 0.4t times ln of e. So here what happens is we end up with this ln of e on the end of the right side. And ln is log base e. So that's log base e of e. In other words, we're asking e to what power is e? And so that's just going to be 1. Whenever you have a log base that matches the number, it's always going to be equal to 1. Like log base 2 of 2 would be 1. Log base 57 of 57 is 1. So ln of e is just 1. And when you multiply anything by 1, it doesn't change it. So ln of e basically just cancels itself out of this equation. And we don't have to worry about it anymore. So that saves us a little time. Now, all we have to do to get t by itself is divide by 0.4. So we have natural log of 160 divided by 0.4. So you got to use the calculator on that. And when you use the calculator on that, you should get approximately 12.69. So that is about 12 hours and 41 minutes-ish. So 12.69 hours, that bacteria colony will grow to a size of 80,000. All right, then this one actually has a fourth part, and I was having some technical problems, and I had to clear the screen here. So we have a clear screen. And what we have to do is graph this function. And to do that, I'm going to start by using the information we've already found. So for our graph, the x in this case is going to be t. That's going to be our time in hours. And our y is going to be n of t, our final amount. And the first thing we saw was that our original amount at time of 0 is 500 bacteria. Then after 10 hours, we plugged 10 hours into our equation, and we found that we had about 27,299 bacteria at that point. Then we started with 80,000. We started with that final amount, and we figured out that was going to be the amount after about 12.69 hours. So we have 3 data points that we can use to make this graph. I'm going to plug in one more just to get a little bit clearer picture, since I've got a big gap from 0 to 10. I'm going to plug in a 5. So what that's going to look like is it's going to be n of t is equal to 500. Sorry about my 5. I can do better than that. I'm sorry. I'm going to erase that. So 500 e to the 0.4 times 5. And that works out to 500 times e squared. And it ends up being about 3,695. Okay, so that's 4 points. I'm just going to do a really rough sketch of what this is going to look like. And I've got to go up to 80,000. So what I'm going to do is I'm going to count by 20,000s. So this first little tick mark is going to be 20,000. I'm going to go up to 40,000, 60,000. And then I'll extend my graph up a little bit. And up here, I'm going to have 80,000. All right, on my x-axis or my t-axis, I'm just going to count by 5s. So I'm going to say I got 5, 10, and we'll go to 15. And so my first point is 0, 500. So 500 on this scale is going to be pretty close to the bottom. So I'm going to say, got a point somewhere right in there. It might even be a little lower than that. I have a point at 5 and 3,695. That's also going to be pretty low. It's probably going to be somewhere, that's probably a little too high for it, but it'll probably be a little lower than that. Maybe let me adjust these down a little bit so we can, I know this is a very just rough sketch of a graph, but we still want to be somewhat accurate here. I erased my y-axis. All right, let's start way down here, and then we'll go up to about somewhere in there. When we hit 10, we're at 27,000 something, so that'll be somewhere in this range. And then when we hit 12.69, so a little past halfway to 15, we're all the way up at 80,000, which is going to overlap with this little box I have. But that's okay, because all we need to know is that this is going to grow like this. And so you can see we have this nice exponential function that shows us the rate at which these bacteria are growing. Okay, last example. This involves these leaf-nosed bats, and I cannot vouch for the accuracy of this information. I kind of did about 2 minutes of research on leaf-nosed bats and then just started picking numbers. But we're going to pretend it's real. So in 2010, we have these 10,000 remaining members of this species. So 10,000 is our N sub 0. And after 2010, the population is decreasing. And that's going to be important. It's decreasing at an annual rate of 4.2%. So R, it's going to be 0.042 because we have to move that decimal twice. So don't forget that 0 after the decimal. But it's also going to be negative because it's decreasing. And that's really important that we make that negative because this amount has to get smaller. So A, we got to find a function to model this population. That's going to be very similar to what we've been doing. We're going to start with N of t. And we're going to say 10,000 bats times E. And then multiply it by our rate, which is 0.042, and then times time. So that's our function. Part B, we've got to figure out what's the population of the species going to be in 2030. So here's something that's key in part A. It says T years after 2010. So T is not representing the year. It's representing the amount of years that have passed since 2010. So when we plug in for part B, and we want to use 2030, we're not plugging in 2030, we're going to plug in 20, because 2030 is 20 years after 2010. So the idea is 20 years have passed since we started observing these bats, and we want to see how many bats are going to be left. So we plug this in. I'm not going to simplify it any more than that. I'm just going to go direct into the calculator here. And when I do that, I get about 4,317 bats are left in 2030 after 20 years. All right, the next question. We go down quite a ways from 2010 to 2030, from 10,000 to a little over 4,300. We want to know, when is it going to hit 1,000? So we're going to do a similar thing to what we did on the last slide. We are going to start with 1,000. That's going to be our final amount here, equals 10,000, our starting amount, e to the negative 0.042 t power. We are going to do the natural log of actually, I'm sorry, we're going to divide first. We want to get rid of this 10,000. That'll save us some headaches later on if we do that now. So we're going to cancel that out. What we're going to get over here is 0.1. And that should happen whenever you're decreasing. When you do that first simplification step, you should end up with a number smaller than 1 on the left side of the equation. Now we're going to take the natural log of both sides. So natural log of 0.1 equals natural log of e to this exponent. We are going to move the exponent out front. Again, this is the key step that makes this all happen. We take that negative 0.042t, we put it in front of the natural log because we're allowed to do that with exponents that are in logarithms. And that ln of e, as before, is equal to 1. And multiplying by 1 doesn't do anything, so we cancel that out. So don't forget to cancel out ln of e. Don't leave it lying around. And now all we have to do to get t by itself is to divide by this negative number here. So divide by negative 0.042. Now here's something you may be thinking. You say, well, I got a natural log of 0.1. If I divide this by a negative number, am I going to get a negative answer? And that would not be good to get a negative answer because we don't want negative years. These bats are not traveling back in time. And the good news is you won't, because when you take a logarithm of a number less than 1, you are going to get a negative number anyway, because that's the only way you can do exponents for things less than 1 is to use negative exponents. So you'll actually end up with a negative divided by a negative. Those negatives will cancel out and you will get a positive. So if you put this in the calculator, as I am doing right now, you will get positive 54.82 approximately. So t is going to be about 54.82. So after about 54 years and 10-ish months, that bat population will have gone from 10,000 down to only 1,000. So there you go. That's modeling with exponential functions. Like I said, there's all kinds of sorts of fun, interesting things we can do with this, but we're going to start with this, see how we do, and then maybe pick it up after the break. So there you go.